Hi, let's talk about unicity distance today. So we looked at between groups, we looked at within groups, and we looked at different quadgrams, monograms, bigrams, trigrams, n-grams. So what we want to look at today is unicity distance. And what this is the property to determine certain cipher algorithms. And essentially what we've done so far is we've determined what language we're likely using, what cipher we're likely using, and how much it differentiates between what we're traditionally looking at as far as uniform distribution. And so we fingerprinted it, we've gotten the language, and we're ready now to start breaking it. However, the unicity distance is going to help determine the minimum requirement or workforce that we need in order to break the crypto system. And this is going to be a lower bound for us. Obviously, it can take more work, and we may skip over the results if we are not certain what we're looking at. But the unicity distance is a good tool to help determine, this is how much work you're expecting, at least. And the reason why it's important is because we don't want to have to brute force for days or weeks or years without knowing how long it's actually going to take. And so how long something's going to take and how much resources and how many requirements are needed to break that system is not easy. We'll see later on. I'll just show you now that the different ciphers have a different amount of keys that are associated with it. So remember we called it the key span, and with the Caesar cipher we looked at a key span of 25 because it goes from A to Z, whether you're looking at uppercase or lowercase, ASCII to value of 65 to 96 or 97 to 122, does not matter. There's the 25 key span. So those are the number of keys. And if you look at different ciphers, they're going to have different work requirements. And so as we transition to quantum and as we transition to modern day crypto systems, we want to be able to determine the amount of work required for this. So if you're looking at quantum, now this is skipping ahead a little bit, you're going to look at something called quantum volume, which is the resources that gives it a competitive edge over classical systems. And it is a unit of measure to provide end users like us or developers the ability to determine how much power we're going to get for our investment. So what the unicity distance is really saying is how much work we're expecting the lower bound to be. And that's what it's really saying here. It's saying unicity distance is a theoretical minimum. And so determining the upper maximum is not easy. I mean, individuals do their PhD trying to figure out the upper bound of certain mathematical or algorithmic work requirements, and it takes a lot of time, it takes a lot of effort, and quite frankly, we're just here to do cryptanalysis for fun, and that is a little more math than what we're required to do at the moment. Later on, I plan on extending SigCryptal to incorporate advanced mathematics for breaking modern day crypto systems, but it's going to take a lot of work, it's going to take a lot of effort, and it's going to be a lot of fun. So let's look at the unicity distance right now. What unicity distance is really saying is it's trying to solve the problem of how many legitimate decryptions we can have for a given ciphertext. So right here we have all the different decryption, some of the different decryptions that you can have for that particular ciphertext. This one up here. And so what we really want to consider here is something called information that is delivered for each bit. And so Shannon early on, let's say during World War II and right after World War II, they looked at information channels. And they were really concerned on, what is the minimum and maximum you can have for an idealistic communication channel. And then obviously determine how much you can have for a noisy communication channel, and you have a quantum communication channel, idealistic, and then a noisy quantum communication channel. And what it's essentially trying to do is provide the amount of information that can theoretically be delivered across telecommunications. So the same thing can be said with crypto systems. And when you're considering different ciphers, you need to consider the amount of information that bit can carry, or that each bit can carry, associated with your key span. For the example given on the website, you're looking at a key span that's associated with the alphabet. So you only have a key span of 26 letters, but you could always have a key span that's larger, and so you need to consider that when you're looking at the amount of work that's going to be done for whatever system you're looking at. In this example, they give some information on the substitution cipher, and once again, it consists of 26 letters, and you're looking at the factorial, and then you're breaking it down by the logarithm base 2 of the 26 factorial, which is the key span factorial, and that's saying that there's essentially 88.28 bits that can be carried across this encryption. And so we could break it down even further and see what the difference between different alphabets or languages are. So English actually has a lot of redundancy in it, and they calculated that each character has 4.7 bits associated with it, but in reality, there are about 3.2 bits per character that are redundant within the English language per character. So this is going to be different for each language, and that information can be looked up, and I would definitely recommend looking that up and becoming familiar with it, depending on which language you're looking at. That will then help determine how long it's going to take to break that crypto system. So the unicity distance is great to know, and we're going to spend a lot of time looking at it for each cipher we do. However, there's a lot of math behind determining the minimum bound associated with the workforce resources that are required to break that crypto system. And if you start linking it to quantum volumes, then you can essentially map with good probability how much work it's going to be and how many qubits are required, or integrated circuits are required to determine the minimum bound to break that crypto system. And so this is fascinating research. It's continuously being done. You can consider it kind of like the branch and bound algorithms, if you're familiar with those. We'll talk about it a little more, but I hope you enjoyed this video. There wasn't any coding associated with it because right here we're just looking at pure mathematics, and look forward to providing the unicity distance associated with the crypto systems we're looking at. And I wanted to leave actually one more thing associated with this. So what I was saying earlier is that you need to make sure you pick a good key, because if you use the English language, then there's multiple redundant bits associated with it, which could essentially make the crypto system weaker based on the key that you use. And that's one of the reasons why NIST recommends having 15 characters for the password with multi-password complexities such as special characters, numbers, um, a difference of character spacing. So you may not be able to have 3 characters in a row, 3 of the same character types in a row. And so that is based on the unicity distance of the particular algorithm you're using so that you don't make the key span smaller and essentially make the crypto system weaker. So it's one of the practical applications of unicity distance, and look forward to applying it more. And if you guys have any comments or concerns, please post them. Please join me on Sick Crypto, and I look forward to seeing you guys. Have a great day.